Hey, in this video we will explore a second concept for passing in data to the shaders. Last time we passed the model matrix to the vertex shader using push constants. Push constants are small values that have to be set by the command buffer for each render command, but they're limited to about 1 or 2 matrices at maximum. We also would like to set the projection and view matrix for our 3D rendering. As I explained, the view matrix is the one responsible to move the whole scene based on the orientation and position of the viewer, and the projection matrix task is to scale the objects from real-world coordinates into rendering coordinates, or to project the scene that is viewable into a 2D image. Based on this description, you might already notice that we don't need to set these for each render command. Actually, if the viewer doesn't move, we don't really need to set these each frame either. So this is where the uniform buffers come into place. They are GPU data that is accessible in the shaders. This data is uploaded similar to how the vertices were uploaded into the GPU. But the data itself is the same for each vertex and fragment drawn within the frame. This will be a two-part process. In this video, we will tackle creating the uniform buffers. In the next, we will create something called descriptor sets. So I start by adding a new file to the source folder. We will call this one uniform transformation.h. Inside, I will add the typical pragma ones. Then I create the veng namespace. I'll spell out a class name that resembles the file name. I call the uniform transformations. And inside we add the view and projection matrix as field members. Next, I will go into the vertex shader. And lastly, here we added this push constants uniform. Well, uniform buffers are pretty similar. And just for a change, I will add them into the common file that is shared between the vertex and fragment shaders. Here I add a layout. Inside the layout we will put set equals 0 and binding equals 0. These are the descriptor sets that we'll be talking about in the next lesson. Next we add a uniform struct called uniform transformations, and it will have the same layout as the C++ struct that we just created. Finally, we give this struct variable name and call it camera. We would like to modify the vertex shader here. It should now multiply the position by the model transformation, then by the camera view, and finally by the camera projection. The ordering here is important, and the position is multiplied from right to left. You first transform the model in its place, then you move it based on where the viewer is, and finally you project it onto the screen. Now we go to the graphics header. Here we will add a new method called createDescriptorSetLayout. I copy it over to the CPP file and create the body. Inside I create a VKDescriptorSetLayout binding. It will be bound to the 0 binding, and the descriptor type will be uniform buffer. It will have one descriptor count. And we need to set the stage flags for which the shaders can use this. We put it in the common GLSL file, so let's have it equal to the stage of graphics. And this layout binding will be part of the bigger descriptor set layout, which we need to create as a member field in the header file. And I will also assign it to noHandle. Now back in the implementation of the new method, we can have a new descriptor set layout create info. I set the S type as usual. Then we can set the binding count. We have one binding, then we pass in the address of the binding info. And finally, we can call vk create descriptor set layout. We start by passing in the logical device, and I have to make the method part of the graphics object. Then I add the address to the layout info, no allocator, and the address to the layout member field. We can exit this if it wasn't a success. So this method can now be added to the initialize Vulkan method. It will be needed before the pipeline creation. And here in the pipeline creation method, we can search for the layout info. And similar to the push constants, we can set two new fields. Set layout count, and then the address to our new member field for pset layout. Now it is important to also not forget to clean up the layout information that we created. So I navigate to the destructor, and here after the swap chain cleanup, I add a destroy descriptor set layout function call. Now on to the next step. In the buffer region in the CPP file, I'll create this new function called create uniform buffers. I create the body, and you know what, this should be a method, so I add it to the graphics header file. This one will create an uniform buffer, and this buffer will be part of the pipeline. So the graphics object should have one more member field to keep the buffer handle. You remember this object that we created for holding onto the GPU memory references. Now, inside the method for creating uniform buffers, we can have a new buffer size, and it will equal to the size of the uniform transformations. This is the new class that we added, and to use it, I also add a header file on top. Next, having this buffer size, we can now call the createBuffer method. We set the vk buffer usage uniform buffer bit, and we would like this buffer to be host visible and host coherent. It will be modified often by the CPU. We will not be uploading this one to the GPU's internal memory. One more thing that we will do is to map the memory, just like with the vertex buffer. We pass in the logical device the uniform buffer handle memory, 0 offset, the size of the buffer, 0 for flags, and finally we will need a pointer that will contain the mapped memory location of this data. We create the pointer as a member field. And this is because we will use a simple trick with the uniform buffers. We will map the memory and we will not unmap it after we copy the data. We would like this location to be always accessible and the GPU shouldn't move the data. Now this buffer needs to be destroyed when the graphics object is destroyed. So I add the relevant call in the destructor. And finally I will add a new method called setViewProjection. This method will take two matrix parameters, one for view and one for projection. I copy the signature and create the body inside the CPP file. Here we can create a new uniform transformations object out of these two values. And then we can memcopy into the uniform buffer location the new values. Now back at the main file we can create the matrices. For the view, let's create a translation matrix. It will translate the camera by 2 units to the back. Let's also create a projection matrix out of this perspective function. First we set the range of view of the camera, which will be 60 degrees. I wrap it in the radians function since GOM expects radians. Then we need to pass the aspect ratio of the screen. It is taken from the screen size, or in our case from the 800 divided by 600. Then we set the minimum viewable distance and the maximum viewable distance. And we can call the setViewProjection on the graphics object and pass in these new values. Oh, and I almost forgot. We created a function for creating uniform buffers, but we never called it. Let's go into the initialize Vulkan method and add it right here in the end. We can then build and run the project, but we will get a black screen and this error. This is because we created the required info in the pipeline for the layout and we created the memory for the uniform buffer values, but we never actually created a descriptor set, which is the object that links both of these together.